Yeah. Ooh, you're killing it down there. I've got to record this guy. What? Why'd you stop? Okay, it's fine, I guess. Oh, he's back at it. You stop. You stop again. Okay, yeah, it's fine. I'll just not record you. I get you don't want to be recorded. It's okay. It really is. You still. Gosh. Alright, whatever. Oh my. No, this skit sucks. It was to portray like the double slit experiment, but it sucks. Did you like it? Quantum mechanics is fascinating. There are so many things about quantum mechanics that make it absolutely astounding. How electrons may push each other away and put them into orbitals that really they shouldn't be in, or how we can really never predict where an electron is going to be. We can, but it's already gone. It's already gone to that place. But what we can do is create an electron cloud. And that's a topic for another day. What I want to talk about today is the observer effect. But first, one of my favorite things about quantum mechanics. If I hit my hand on this remote, there is like a 1 in septillion odds or something like that, that my hand goes through the remote perfectly. And there's a much higher chance that I hit the remote and my hand only goes part way through. And my atoms are completely intermingled with these ones, so there is no medical surgery that is getting me out of that predicament. But it truly is fascinating. Now, the topic of today's video is the observer effect. The observer effect is, I think it's probably one of the most well-known quantum mechanic ideas ever. So, the observer effect is we watch electrons being shot through the double slit experiment, which I will talk about in more detail in a minute. And when we have something recording it, not that when we look at it, it doesn't show up, but it's when we try to record the movement of the electrons that something weird happens. So let's take it back. What inspired us to do this? Now, since the beginning of time, or not the beginning of time, but since the beginning of atomic theory and the study of what photons are, we've been trying to determine, is light a wave or is light a particle? And we've also been trying to determine the same thing for electrons and atoms. Now, what is so amazing about this is it wasn't even solved until really recently. It was only solved about 100 something years ago, where we decided they're both. Both of them are both at times when they feel like it. And what determines that? Don't ask me. I'm here to talk about the double slit experiment. So the double slit experiment is where we're shooting a light beam, and we're shooting it at this wall, and it has 2 holes in it. It has 2 holes, and they're the only holes for entry, and we have like 6 or 7 different really really energetic rays. Like they are really popping on the wall, along with obviously somewhat of a gradient. And it's so cool, and this was one of the first things to really solidify that photons can act like a wave. How do we know this? Well, when a trough meets a trough, so when the bottom of one wave meets the bottom of another, they amplify each other. When a crest meets a crest, so the top of 2 waves, or somewhere near the top, meets each other, they amplify. So it's 2 positives and 2 negatives will amplify each other. Now a positive and a negative, they cancel each other out, and that's why there are more that's why it's somewhat of a gradient in places. That's why there are dim spots in where the light should be. And so how does this apply to atoms or electrons? Whatever we're shooting through. Well, we take an atom gun and we start shooting, but this time we're only shooting through one hole. We're covering the other one. And this is because we want to see what happens when we have explicitly one hole. So, As you see, there is one single concentrated slit, and then there are several other sections where it's somewhat, dotty and like all over the place and scattered. And that could be a multitude of reasons. Maybe they were bouncing off of each other. Maybe there were intermolecular forces we didn't know about. Maybe they just bounced off of like the slit. Who knows? There are so many reasons they could have been in those places at those times, which would have them recorded. Now, we open up the second slit, and this is where things get interesting. When we open up the second slit, we make a huge observation, and this observation is going to change quantum mechanics forever. We see that it acts the same way the light did, and it acts as a wave. There are times where it's amplified, and there are times where it's pretty dim. And we see the same thing the light did, where there are atoms being scattered in places somewhat like a gradient, and then we see that they're very concentrated like sections, the same way the light was. And so then we're going to take it to the next step. What if we shoot it really slowly? We track the movement the best we can with our eyes. Obviously, we can't see electrons or atoms like that, but when I say that, we see where they land. We track them the best we can. And it starts off with, we're shooting one, we see where it goes on the wall. We shoot another one, we see where it goes. And we do this a lot more times. And we obviously can't watch the atoms themselves, but we are seeing that very slowly, all of their sections are being filled up the same way they were when they were being shot rapidly, just way slower this time. So then we think, what if we try to watch the movement of electrons? So we set up an observer, and we set up the observer specifically to the top slit. And when the top slit has an electron enter through it, we hear a ding, and we should hear it 50% of the time. And we do. But what we observe on the wall is not what we expect. We expected to see the 6 or 7 concentrated areas, but we see something completely different. We see what we should have expected from the beginning, where there are 2 very concentrated bands with things in between, things on top, things on the bottom. But why? Well, we don't actually have an answer, but my answer is that I think there's an electromagnetic radiation thing happening. Electromagnetic radiation are waves given off by microwaves, radio waves, and any of technology that we have, including the phone or the computer that you're watching this on, have electromagnetic radiation coming off of it. It has waves coming off of it. So, what I think is perhaps the waves did something to the waves that the electrons were giving off, and it disrupted them. So instead of having these areas where crests were meeting and the troughs were meeting, it disrupted the waves and it led them to go straight forward where they were being shot, not towards all the amplified parts like we saw with the light and the other 2 experiments, or 3, however many I've done. And so it's amazing. This is an amazing experiment, and this is one of my favorites. And one day, maybe I'll talk about quantum tunneling some more, but I believe my next video should be about general and special relativity, Einstein's theory about how gravity bends space and time. Look out for that.